applications of quadratic functions. Our objective for this video, we want to solve problems. We're going to be talking about kind of real life problems involving a quadratic function's minimum or maximum value. Let's think about it. Any projectile will have a graph that is parabolic. Okay, so we can write a quadratic function for any projectile. If you're thinking about, for example, way back when shooting cannons, cannonball is going to be a quadratic. Shooting a rifle, it may not be quite as high, but it'll be a quadratic. It'll be a parabola. More commonly, you'll see this in a lot of sports. All of your baseball home runs go up and down as a quadratic. In football, if you're punting the ball, which is going to be the example we do today, it'll go up and down as a quadratic. If you're shooting missiles at things in the military, it goes up and down as a quadratic. So all kinds of stuff, and obviously a lot of these quadratics are opening down in real life. But the quadratic function is behind all of them. The graph of the quadratic is what you see, which is that upside down bowl. So let's do some real life stuff. What do we know? We know what a quadratic function is. Any function of the form f of x is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. When the function is in general or standard form, well, that's the form we have that we see most often. That's the general or standard form. The vertex has an x-coordinate of negative b over 2a and a y-coordinate of the function's value at negative b over 2a. We've done that in prior videos. The parabola is the graph of any quadratic. It's either going to be like a bowl or an upside down bowl. And the coefficient of the x squared term, the a, determines whether it opens up when a is positive or it opens down when a is negative. The vertex is what we're chasing in a lot of these problems. That's where the parabola makes its turn. If the vertex is a minimum, the parabola opens upward. Or if the parabola opens upward, the vertex is a minimum. Otherwise, the parabola opens downward, our vertex is a maximum. And we're going to be focused here with this example and a lot of things in real life because of gravity. Gravity forces things that get thrown up, shot up, to come back down in a parabolic arc. Very popular. And we learned in a previous video as well that the x-coordinate of the vertex represents where the minimum or the maximum value is. And again, we'll be focused on a maximum value in this example. The y-coordinate of the vertex represents what that maximum value is. And we'll see that clearly with this football example. Let's take a look. Most real life problems involve finding the minimum or maximum value as well as where it occurs. And again, because of gravity, you get a whole lot of this one. Okay, projectiles. You get a whole lot of finding maximum values in real life. So our example, a punted football. The height of a punted football will be f of x in feet. And here's how it's modeled. F of x is equal to negative 0.01 x squared plus 1.1 times x plus 2, where x is the football's horizontal distance in feet from the point of impact with the kicker's foot. Okay, so x is the horizontal distance, which of course when it gets kicked is 0. When it's on the foot, we're at 0. F of x is how high the ball goes as it goes out horizontally. Okay, so what's the maximum height of the punt? You want to write kind of small here if you can. There's not a ton of space. I'll try to, it does work. Just for those who have big handwriting, you might want to be a little bit smaller if you can. Okay, so what do we know? We know that A is equal to negative 0.01 that is less than 0. That means it opens down, and that means the vertex is a max. But we knew that because this says what is the maximum height. So we knew we had a max. I'm just pointing out that the coefficient of the x squared term is negative, which means we have a maximum value. Okay, so what is the x coordinate of that maximum value? Okay, let's see here. I'm going to leave a little space here to draw a picture, by the way. So the x coordinate, if I can, let's see here. Let's try to write that again. The x coordinate, okay, is equal to negative b over 2a. We've done this before. If we go back up to what we know, okay, when the function is in general form, the x coordinate of the vertex is negative b over 2a. Let's go back to here. Again, make sure I've got all my paper showing for you. Negative b over 2a is negative, well, b, and again, I use parentheses, is 1.18, and it's 2 times a, which is negative 0.01. I'll do that math in a calculator, and I come up with 59. So, how far, where does the maximum height take place? 59 feet from where the ball hit the punter's foot. The punter kicks here. At 59 feet away, the ball has reached its maximum. What is that maximum is the y coordinate. Okay, that is f of negative b over 2a, which is the same as f of 59. Okay, because negative b over 2a is 59, which means we've got to put 59 into our function. So negative 0.01 times 59 squared plus 1.18 times 59 plus 2. That goes into a calculator, and I came up with 36.81 as I rounded to the 100th. Okay, feet. All right, so what do we know? Let's draw that. We're in real life, so we're going to draw in the first quadrant. Okay, so what happened? The ball left from the punter's foot. It left from about here. The punter's foot, of course, is a bit off of the ground when the punter hits it. The punter's foot is not on the ground. We're punting. So the punter's foot is here, and the ball goes like this, and then it will come back down in a parabola. And we're told the maximum takes place 59 feet away from the punter's foot, and it hits a maximum height of 0.81 feet. So it looks something like that. Okay, so what is the maximum height? The maximum height is 36.81 feet. And how far from the point of impact? It occurs 59 feet from point of impact. Again, think of the punter. The punter drops the ball hits the punter's foot as the punter begins to kick. So it's a little bit above the ground. We're not kicking a field goal, we're kicking a punt. The ball then goes up, hits its parabola, and comes back down right there. Okay, so the maximum height is, where is it located? It's 36.81 feet. Excuse me, where is it located? The maximum height is 36.81 feet. That's the y direction. What is the maximum height? Where does it occur? 59 feet from the point of impact, and that is in the x direction. Okay, let's go back to here. Whoops, wrong paper. Let's get myself to this one. Okay, I went to the wrong side of my paper. Excuse me. Okay, we got a part B and a part C to this. We got a defensive player in part B. This player is 6 feet away. Get my sheet a bit lined up here. 6 feet away from the point of impact, so essentially 6 feet away from the punter. And this defensive player jumps up to block the punt, to attempt to block it. If this defensive player is going to tip the ball or touch the ball, how high does he need to jump? Okay, well, let's take a look at this in a graph. Whoops. What's happening here in the picture? Okay, here is my graph. Again, my ball left from a little bit above the ground. My ball went up, hit a maximum height, and then my ball is going to come back down. And we know that this distance to the vertex was, let me remind myself of that distance. Where did I put that? This distance was 59 feet away where it hit its maximum value. Well, our punter's only, our defensive player is only 6 feet away. But the ball has obviously gone up between the point of impact and the 6 feet away guy. So this is the question. How high? What is this Y value right here? How high does this person need to jump to touch the ball? So the question basically is, again, let's remind ourselves of the function. The function says you can find the height by using this quadratic equation, O1x squared plus 1.18x plus 2. Okay, what is the height of the ball when the x distance, the distance away from the punter's foot, is 6 feet? Well, let's simply put 6 in for x. So put 6 in here. We'll place 6 into here. Notice again my use of parentheses, and there we have it. Well, that's a calculation. All I need for a calculation is a calculator, and out comes to the 100th 8.72 feet. Okay, so when the ball is 6 feet away from the point of impact, its height has gone from wherever it was at the beginning, which is 2 feet actually, it's gone up to 8.72 feet. So this defensive player needs to be able to jump 8.72 feet to get his finger on the ball to begin to have an impact on that, just to touch it at 8.72 feet. Okay, let's go to part C. All right, let's go to here. Excuse me for a moment. All right, if the ball is not touched, a defensive player can't get up there. How far down the field will the ball go before hitting the ground? And we're going to assume that the ball is not caught by a punt returner. Okay, the punt returner maybe decides to wave his hand and let the ball bounce. So how far does that ball go before hitting the ground? Well, let's take a look at a picture of that. So here's our first quadrant. The ball gets kicked a little bit, it's not on the ground, a little bit above the ground. The ball goes up and forms a parabola, and it comes down, and right there, where's it hitting the ground? Okay, it's somewhere out here. We know that at 59 feet is when it hits its maximum. Well, how far does it go to when it hits the ground? What's going on there? So, what do we know about hitting the ground? Well, let's first note our function. F of x is equal to negative 0.01x squared plus 1.18x plus 2. Well, we know when it hits the ground that the vertical distance, which is f of x, is 0. It's gone from here, and it's hit 0 in the vertical direction. Well, that's this part. So we want this, we want to solve this, we want to find the zeros of this function. Gets back to an x-intercept, which are the zeros. So we want to solve this equation. That's the equation we want to solve. We want to find what x is when we're back on the x-axis, when we've hit the ground in this case. Well, I'm going to write it with, I'm going to reverse this and write it in reverse because I like to see things with the x's on the left. So no big thing, it's just kind of my preference. I like that better. So So I just rewrote this and I just switched the two. Well, is this factorable? I have no idea, but I'm not going to play with it. There's too many decimals and other mess going on here. So this calls for the quadratic function. Every quadratic can be solved using the quadratic function. Negative b plus or minus square root b squared minus 4ac, all divided by 2a. So let's put in our points. So b is 1.18, so negative 1.18. I'll use parentheses, plus or minus the square root of b, 1.18, squared, minus 4 times a, negative 0.01, times c, which is 2. All of that over 2 times a, and again, a is negative 0.01. So I'm going to put this into a calculator. It's a calculation. And I'm going to first do the plus, and I get an answer out. So negative 1.18 plus this, okay, divided by this. I'm not sure which one this is, but I'll put one answer I know is negative 1.7, or, and maybe that's the minus, I don't remember exactly, but I'm going to get two answers out. Let's do the negative 1.18 minus this, divided by this, and out comes 119.7 to the nearest tenth. Well, obviously, we're not using the negative one. What that says back here, as you notice, is if I come down, if the punter had kicked it from, well, the punter kicks it at 0 feet above the ground, so there's the negative x-intercept, the negative 0 back here, which we're not concerned with. We're concerned with this one. How far did it go out? And right there is the answer we got. Okay, so how far down the field? It will travel from the punter's foot. Let me come up a little bit. It will travel approximately 119.7 feet from the point of impact. Okay, let's see that on our graph. Hang on a second here. There we go. I think is my function in there? No, my function not in there. Let's go back in my y equals and clear out my previous function. Here's the new function. Negative 0.01 x times x squared plus 1.18 times x plus 2. Now I know in my window, I mean, I'll zoom standard, but I know this is not going to work because it's way too, the football, see, there you go. It's showing me a lot. I want to be in the first quadrant, and I'm really tight here. So my window, I want to go from a maximum of 0, and I know I'm going to want to go about 120 feet, so I'll go 125 feet. And I'll count every 25, my tick marks. And I know my y minimum, well, it's 0, because that's the ground. Let's put it -1 so we can see it a bit more clearly. I'll put -5 in there. And I'll max out, well, I know it reached, I think it reached 39 or 40 feet or something. Let's go to 50. And I'll count by tens. Okay, here's my graph. There we have it. Okay, so point of impact. Notice it's a little bit above the ground. The origin is just below that. So there's the point of impact, there's my max, and there's where it touches. So let's find that point right there. So second calc, a 0. But I want the 0 that's over here to the far right, where the punt hit the ground. So there's a right bound. And now I need to go a bit below the ground, so to speak, and there's a left bound, and give me a guess. 119.67125 feet, which I rounded to 119.7. So there's the ground at 0, and there's your 0 of 119.7 feet. So there you have it, an example of how we use these things in real life.